I'm going to do another example of designing a lead controller. And I'm going to go through this one pretty fast because we've already gone through another example. So I'll be doing these steps pretty quickly. Here's the plant, uncompensated plant transfer function. You look at it, you see it's a type 1 because it's got one pole at the origin. Let's see the G sub naught, rid of that. Set the other S's to 0. I just get 1 over 1 or 1. So G sub naught evaluated at 0 is 1. So step 1 I can do without a Bode plot. By the way, what were the specs here? A peak overshoot spec under 30% and a steady state error to a ramp of 20%. We find the K sub naught from the steady state error spec, and we can find that without a Bode plot. Steady state error is 1 over K sub V. That's 20% or 0.2, so that we calculate the K sub V is 5. K sub naught, which we need, is that K sub V over this G naught, actually evaluated at 0 here, which was just 1, so we still get a 5. In dB, that's 14 dB. So if we had the original Bode plot, we'd have to put a reference line 14 dB below 0 to get the new 0 line. Or we could just draw or have MATLAB do our Bode plot to already include this K sub naught. And by the way, when I did all this, when I learned all this back in the Stone Ages, we didn't have MATLAB or any other computers. Everything was by hand. We had to draw the Bode plot by hand. We had to draw the reference lines by hand or put them in our head. All this had to be our own charting, our own sketching. Now we have MATLAB, so I'm going to speak to MATLAB. So this is the Bode plot after step 1, after we find the K sub naught. Let's see, where's look at the 0 dB line, go to where the blue line crosses. I'm out here at almost exactly 2 radians per second. 1, it's 2. And you can see the phase margin is almost nothing. Here's the minus 180. We're almost crossing at minus 180. MATLAB calculates it at 4. It should be a 4, not a minus 4. Pretty sure. Maybe it is minus 4. Pretty close to 0. So we're going to have to add quite a bit of phase margin. What phase margin do we need? Peak overshoot spec was 30%. Here's our 30%. Come over to the blue line. It's about there. That's about 40 degrees of phase margin. This is all based on a prototype second order system dominant pole concept. From that 40 degrees of required phase margin, here's the formula for calculating the phi sub m, how much our controller needs. I guess that was a 4 degree phase margin. That comes up to 46 by our formula. Bump it up to the nearest increment of 5 degrees. Bump it up to the nearest 5 degrees. I get 50 degrees. From there, I can calculate my A. It says A is 7.5. We'll bump that up to the nearest whole number. A equals 8. And for use in step 5, 10 log of A is about 9 dB. So here was our Bode plot after step 1 to include that K sub naught. I need to go another 9 dB down. It's kind of hard to see exactly on this increment here, but I'll say it's about there. Come on over. I hit the blue line there, which is down here at 1, 2, 3, 4 radians per second. Our omega sub m, which is found graphically, you can't just calculate it. You can calculate the 9 dB exactly. You got to use the Bode plot to get the omega sub m. Now we can use formulas to find the Z and P, crank out the formulas. Here is our lead controller based on the numbers. Now all we need to do is check it out with MATLAB. Do we meet the specs? Put it in there, and let's see, our phase margin is only 37, not quite 40. Shy of our goal of 40, so we do need to iterate. We can't change the case of not without violating the error spec, steady state error spec. So we got to repeat the steps where we're finding the P and the Z. The A of 8 got us to 37. I'll bump up the A a little bit. Seems like we're not that far from 40, so I'll bump 8 up to 10. I can also think of that as adding more to that phi sub m. A phi sub m of 55 degrees, get this at 10. But I could have just bumped the A directly. It gives us a new omega sub m. I won't go through that. Get a new P and a Z, and okay, let's see if that's enough. It only gets us to a 38-degree phase margin. So let's bump things up again. In this case, I bumped the P up. I'm going to bump the A up. I'm not going to go through this in fine detail. We're just iterating at this point. At least on the Bode plot wise, after this iteration, we're barely meeting our phase margin spec. We wanted 40, we got 4. Is that enough to actually meet our peak overshoot spec? No, we wanted it 30 or under, and we're at 30.9. So we'll go one more time of iteration. I bumped up P a little bit more, which also gave us a bigger A. And we're finally meeting our spec. Anyway, some lessons of all that, of all this using Bode plot. There's a lot of approximation involved. Don't expect precision. It's usually okay to round things up, round things off, but if you round them off, round them up. Somewhat different values can still meet your specs. Yeah, this is not a case of precision. You might need to iterate. I think the homework problems I gave my students could be done without iteration. By the way, there's no guarantee that we can meet all the specs with a lead controller. But when I gave problems, they could be met. And I told my students to concentrate on the steps before you check it out with MATLAB. Can you just design by the numbers? And here's like things on a formula sheet. The only thing not quite on the formula sheet is this omega sub m. You can find the A, but the omega sub m is found graphically. The rest of it is using these formulas. Put them on a formula sheet. In another video, I'll talk about how to translate different kinds of specs other than steady state error and peak overshoot into what we need to find the K naught and the phase margin. Anyway, that's through 2 examples. Almost done with Bode. Almost. One more video.